If you've been doing electronics for a while, and you're also interested in recycling old components, specifically magnetic cores, there is quite a high chance that you have amassed a collection of various shapes and sizes, which, other than the color, you know nothing about. Hello, and welcome back. Today, I want to look at how the main properties of unknown closed-circuit magnetic cores can be measured. I will be looking at how you can figure out the inductance factor, how many turns you need to get a specific amount of inductance, but also look at how the complex permeability can be measured to determine what the actual usable frequency of the core is. So if you're curious about that and much more, then keep watching. So let's start off by discussing the meaning of the parameters that we will be measuring today. First, AL, or inductance factor value, is a parameter specific to a core, which is used to determine how many turns you need to get a specific value of inductance. This definition is also the way in which you determine this parameter. You coil a few turns over a core, measure the inductance, and from this you can determine the AL value. Now, you could of course just make a single loop of wire, but usually it's a good practice to do this with multiple turns to make sure that the magnetic field is well distributed throughout the core. Then, the other main parameter of interest today is the complex permeability, and specifically its two components, the real and imaginary part. This is a material property, and specifically we will be looking at the series terms. These are commonly used since these help convert a specific inductor into its equivalent series model at a given frequency. So the series resistance is determined from multiplying the pulsation times the baseline inductance and the imaginary part of the complex permeability. And for the reactive bit, you use the real part of the complex permeability. While you will not always be interested in the exact equivalent model, the main utility of knowing the complex permeability over a frequency range is to determine what an inductor will actually be good for. So up until a point, the real permeability, the reactive component, is dominant. This means a coil used in this frequency range is an inductor. It's good for power converters or whenever you need inductance. While in the second part of the graph, the imaginary permeability dominates, so the coil behaves more like a resistor. It turns RF into heat. So a coil used in this range is quite good for filtering or as a choke. Knowing this property is therefore critical to select the right core for the right application. Now, getting the inductance factor is quite a straightforward process. You need a few turns and an inductance measurement. This will work with any core shape. On the other hand, getting the complex impedance value is a bit more complex and will mainly be possible with a closed magnetic circuit. Things like toroids. Also, there's a bit more math and measuring involved. First thing we need is the initial permeability. This is a material property which is commonly cited when looking over core datasheets. So knowing this will also help in identifying the exact material type we have at hand. The initial permeability can be determined if we know the inductance of a coil, its number of turns, as well as the effective magnetic length and effective magnetic cross-section. Specifically in the case of a toroid, once you measure its dimensions, the proper way is rather complicated, but you will need this to extract the parameters. Now, if you don't want to be bothered with the mathematics, you can always use an online calculator like this one from Ferrite. So this takes the magnetic core dimensions, as well as the number of turns, and the measured inductance, and once you hit enter, it calculates the various parameters. So things like your magnetic length and area, as well as the initial permeability. And you also have a set of formulas for reference based on which this is done. So doing something like this makes life a bit easier than just crunching the numbers by hand. Moving on, for the complex permeability, you need to first measure the series resistance and reactance of the coil at each frequency of interest. And then, using some of the values we already determined, like the initial permeability and the tested coil's inductance, you can finally extract the complex permeability terms. This calculation will usually be done in a spreadsheet, where you can analyze large sets of complex impedance data and finally plot it out in the shape of a graph. So now that we have a good understanding of the parameters we will be working with today, we can finally proceed to measuring them. But as with everything else, it's not that easy. There are a few things to keep in mind to get a good result. So there are three main tools I will be using for today's measurements: a caliper, an RLC meter, and a vector network analyzer. Each of these have their own strengths and weaknesses. The RLC meter is special because it provides an easy way of measuring inductance at low frequencies. Each device is different, of course, but most common RLC meters work from about 100 Hz up to about 100 kHz. The VNA, on the other hand, again, while it's device dependent, will usually work at much higher frequencies. So this particular model can measure from 50 kHz up to a few gigahertz. And the caliper, well, let's just say it works in DC. You will need this to measure the physical dimensions of the core. A micrometer could also be used for added precision of small sizes. So the first question to address is, which of these devices are really needed? And well, the short answer is all of them. Last theoretical aspect to discuss has to do with how the number of turns impacts the measurement result. So the complete model of an inductor contains an RL series circuit, but also a parallel capacitor. If we plot out the impedance of this, we get a deformed triangle which has a peak at the inductor's self-resonance frequency. Now, if we decompose this measurement into inductance and capacitance, because of the way the capacitive and inductive reactances interact, right around the self-resonant frequency, the measured values become different from the actual values used in the model. So if you want to find the actual inductance of an inductor, you need to be well below the self-resonant frequency, by at least 1 decade. The other thing to consider is the fact that the capacitance of the inductor is dependent on the number of turns. If you have just one turn, you get very small amounts of capacitance, but also very small amounts of inductance. The SRF appears at high frequency values, but the impedance is quite difficult to measure at low frequency. On the other hand, when you add a lot of turns, you first increase the inductance, but also the capacitance. This moves the SRF way lower. The point is that you want to keep the number of turns as low as possible while still covering the core uniformly, and using low capacitance winding techniques to achieve the best result. So, to start off the measurement session, let's evaluate 3 different winding techniques to see what sort of benefits you can get based on how exactly the coil is built. All of the cores are the same, and the coils have the same number of turns, so 6 in all cases, but each are built differently. And just to get an extra set of validation data, I used 2 different types of cores, one with a relatively low permeability value and one with a much higher permeability. So the first coiling technique is just the typical way of winding a toroid. You start at one point, go around the tor, and then end up in the same place. You should not expect any special benefits from this, but there is beauty in simplicity. The second technique is referred to as the split coil winding. Here you start at one end, coil half the turns, then switch to the other side, and coil the rest of the turns. This is supposed to reduce circumferential current, but also the parallel capacitance should be much smaller since the coil starts and ends at opposing sides. The third method involves coiling 2 coils in parallel, both starting at one end and ending at the other. So while there are 12 turns in total, it's 6 in parallel with 6. But since they're on the same core, the end result still behaves like a single 6-turn coil. This should also reduce circumferential current, but you might have an adverse effect on capacitance since there is far more surface area. We'll just have to see how this works. Now, I'm not going to get any surprises, since I know exactly what the cores are. I have their exact properties, since I have the order code and the manufacturer provides a really good datasheet. This is quite important data when testing out a measurement technique, since if you get the values that you are supposed to get, then the measurement method is probably good. First, to get an idea of the AL value of the cores, I used an RLC meter. While you could measure at any frequency, the general recommendation is to measure with a low frequency, but still have a good measurement resolution. The higher the permeability of the material, the lower the test frequency should be. Now, for this test, I used 10 kHz, since this is what the datasheet of the cores used in their characterization. And after going through all of the cores, I got the following set of data, as well as the datasheet references to which we need to compare. Now, all of the measured values are slightly different, but it's important to accept that the core materials, as well as the physical shapes, do have tolerances. The TDK datasheet mentions about 30% of tolerance, while the ferrite one mentions 25%. So, by that interval, all of the measurements are well within their acceptable range. However, it's important to observe that the values did vary in the same way. The smallest value was observed for the normal winding, while the largest value was present on the split windings. And the parallel coil was somewhere in the middle. So the coiling technique will probably have a small impact on the observed inductance. Next, it was time to do a bit of mechanical measurements. This is needed to get the material's initial permeability. So now, taking all of the data we have, including an average of the AL values previously measured, I used the online calculator to crunch the numbers, and got the following initial permeability values. For the TDK core, I got a rather low value, but still within the 30% tolerance, so it's acceptable. And for the ferrite core, I was much closer to what it was supposed to be. So all in all, while I didn't get the exact datasheet values, these are still within limits. Now, to get an understanding of why one was so far off while the other wasn't, an important clue lies in the effective area and effective length values. For both cores, the effective length is more or less spot on, but when looking at the effective area, especially with the TDK, I'm getting a much larger value than what the datasheet said. This can explain the lower calculated permeability value. Now, the calculations expect the core to have a perfectly rectangular cross-section, but in reality, this is not the case. Both cores have some degree of chamfer cutting up the edges. For the ferrite core, this is less pronounced, but for the blue core, this is much more visible, so we have a very obvious rounding of the edges. And while the second problem with the blue core is the color. Ferrite is not blue. In other words, there's a layer of paint over the underlying ferrite material, which means that the actual core is smaller than what you're measuring. You can assume about 100 micrometers of paint, but to get an exact value, you will have to cut up the core. This is not really a problem with large cores, but this is quite a small component. So here, this becomes quite problematic. So far, the measurements seem to be more or less the same, regardless of how the coils were constructed. Some deviations were observed, but nothing major. So now, let's see what the higher frequency behavior of these components is like. For this, I turned to the VNA, and the first measurement was to look at the point where the reactance crosses the 0 mark. In other words, where the self-resonant frequency is. When comparing the cores, while there's no exact reference to validate, we can still observe that a similar behavior is appearing. The split winding seems to have the lowest parallel capacitance, while the parallel winding seems to have the largest parallel capacitance. So if you're trying to maximize the usable frequency range of a particular inductor, this split construction should be the best. It's still important to notice though that the wire is not all that close to the core. The actual split gets the wire floating for a short period. So not all of the magnetic field is going through the core. Now, while the parallel winding did seem to behave quite poorly, at least from a capacitance point of view, it's still important to observe that we have double the number of turns. In other words, the magnetic field is far better contained and distributed inside of the core compared to the other two winding techniques. While this is not particularly obvious with 6 turns, if you have fewer, say 3 or 2 turns, then you won't really be able to properly cover the core with the normal winding technique. But the parallel winding thus become superior. So in certain cases, this sort of winding will be better. For the final measurement, the complex permeability, it's time to do some spreadsheet math. The measurement was done with the VNA and saved as an S11 parameter file, but the actual processing will be done in tables. The coil I used for this was the parallel coil. Now, the VNA that I have saves the S parameters as real imaginary pairs. So the first step is to convert this into series resistance and reactance. Now, if your VNA can save data like this to begin with, you can skip this step, otherwise you'll need to apply these formulas. So that's what I did for every single frequency point. From here, we need to know the measured inductance as well as the initial permeability data of the core. So we have this from our previous measurements. And then by running this second set of formulas, we get another large set of data. So this is our real and imaginary permeability. And we can take this and plot it in the form of a graph. Now, the datasheet will usually present the permeability on a logarithmic scale, so not on a linear scale. So we can also do this conversion quite easily. However, it's important to check what the smallest values that you're getting really are. So this is not really a problem for linear scales, but for logarithmic scales, you cannot plot negative values, and you can't even plot 0. So you need to define some sort of minimal value. So in this case, I set a minimum value of 10, and then I added an extra processing step in which each of the values are compared to this minimum. If the value is larger, you actually plot the calculated number, otherwise you plot your minimum. And finally, we get this sort of graph. Now, looking at our actual cores, I did the same process for both of my cores. So first one to look at in more detail is the one from ferrite. So this is a type 61 material. I know that from the order code. And well, if we check the permeability graph and compare it to the actual datasheet graph, we can see that the measurement is in quite good agreement with what it should be. The general shape, as well as the various inflection points, are all in the right place. Even the exact values are almost identical to what they should be. So in this specific case, we have a very good correlation between the experiment and reality. Now, if we look back to the other core, so the TDK one, this is a type 37 material. While the exact values are off a bit, this is because of the lower permeability that was measured, the exact shape of the graph is still good. So it's important to observe that while you may not get the right numerical values, you can still get the correct shapes. Therefore, you can still reliably say what the actual usable frequency of the core is, even if you don't have the exact numbers. In the end, measuring unknown magnetic cores is not all that difficult as long as you pay a bit of attention to the test setup. While most materials have quite a bit of tolerance, and there's even more tolerance introduced from the actual measurements, you can still get reliable data. You can easily determine the inductance factor as well as the usable frequency range of a specific core with not all that expensive equipment. So all those cores you've collected over the years can finally be put to good use. And with that said, I hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.